Good evening, everyone. We are Group 10 from Section C, and today we will be presenting one of the most foundational concepts in computer science, the Turing machine. Before we begin, I would like to introduce our team members and their roles. Abdullah Ahmed Khan and Sayyid Yusuf Minaj gathered all the relevant material for this project, while Sayyid Azlan Ali compiled the final presentation in PowerPoint form. My role has been to compile and present this voiceover script. Our presentation is titled Understanding the Foundation of Modern Computing. We aim to walk you through the concept, importance, and the lasting legacy of Alan Turing's theoretical model. The Turing machine is one of the most fundamental models in computer science. It was invented by the legendary computer scientist Alan Turing in 1936, whose work continues to influence modern computing even today. Its purpose was to define rigorously what functions are computable. It formalized the concept of algorithms and computation, providing a concrete foundation for computer science. Even though it's a purely theoretical model, the Turing machine laid the groundwork for every modern day computer. Anything your smartphone, laptop, or supercomputer can calculate, a Turing machine can also calculate if it's given enough time and tape. What is a Turing machine? A Turing machine is an abstract model of a computing device that performs operations step by step according to the rules we give it. It has four main components. Number one, a tape. A tape is an infinite strip divided into cells for reading and writing symbols. Number two, head. It reads symbols, writes new ones, and moves left or right. State register. It holds the current state of the machine, determining its behavior. Transition function. Rules that decide what the machine does next, what to write, where to move, and which state to switch to. These simple components allow the machine to perform very complex computations, forming the blueprint for universal computation. Step 4. The working principle. The operation is very straightforward. It scans the tape symbol under its head. It then writes a symbol. Then it moves the head either left or right. Then it changes to a new state. This cycle repeats until the machine reaches a halting state, signaling that the computation is complete. Think of it as a rule-following robot that can perform any computation if it is given enough time and tape. Its importance and uses. The Turing machine's significance goes beyond history. Number one, defining computability. It provides a rigorous framework for what problems computers can and cannot solve. Theoretical foundation. It underpins automata theory, formal languages, and algorithms. Number three, programming language design. It proves that a universal computing device is possible. Understanding Turing machines helps computer scientists reason about the capabilities and limits of all computers, not just the ones we have today. The variants and extensions. There are several variants. Number one, multi-tape Turing machine. It uses multiple tapes for faster computation rate. Number two, a non-deterministic Turing machine. This Turing machine basically has choices between moves, which makes it possible for it to explore paths simultaneously, like quantum computers. The most important one of them all is the Universal Turing Machine, also known as the UTM. It can simulate any other Turing machine by reading its description from its tape. It is the conceptual basis for modern stored program computers. The UTM proved a single machine can perform any computation given the correct input and program bridging theory and real world computers. The limitations and modern relevance. Despite its powers, the Turing machine also has limitations. For example, undecidable problems. Some problems, like the halting problem, cannot be solved by any Turing machine. Practicality. It is a theoretical model. It is not meant for real world computation. Yet, its modern relevance is undeniable. Hardware and software. It influenced the CPU design and programming logic. Number two, architecture. Stored program concepts are derived from the universal Turing machine. Number three, legacy. Turing's work continues to inspire artificial intelligence, cryptography, and computational theory to this day. Its practical examples in real world computing. Real world applications show Turing machines' influence, such as the compiler and interpreter, which translates source code into machine code, functioning like a universal Turing machine. Finite state machines. They are used in vending machines, traffic lights, and game logic. Each state change mirrors the Turing machine's transition function. Artificial intelligence. AI processes input data, it applies rules, and then it produces an output. It basically follows the logical principles of a Turing machine, which Turing defined. These examples show how a theoretical model underpins everyday technology. The conclusion and closing. In conclusion, the Turing machine, invented by Alan Turing in 1936, is a simple yet powerful theoretical model. It formalized algorithms, defined computability, and it is a conceptual ancestor of all modern computers today. Its universal Turing machine laid the foundation for stored program computers, and its principles continue to influence fields like artificial intelligence, cryptography, and the computer science theory. The video format we have chosen for this project is MP4 because it provides high quality video while keeping the file size small. It is also very easy to share and plays on almost any device or platform. It is the most widely supported format, working smoothly across Windows, Mac OS, iOS, and Android, along with other operating systems. An alternate to this would be AVI, but it creates very large files which can be very hard to manage. Alternative number two can be MOV. It works well for Apple devices, but it is not as compatible on other systems such as Windows or Android. Thank you for your attention. We are now open to any questions.